Thanks. We got nitrogen with 5 dots. 1, 2, 3, 4, 5. X, X, X. Those are H's. All right. F2 dot X dot 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 X, 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 X. And then C. I'm gonna reverse it here. I'm gonna use X's for C just because it's a lot easier to make a lot of dots than X's. All right. So there's my I. My 4 I's, and 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So every atom here has 8 dots or X's around it. Remember, they share the ones in the middle. So carbon has 2, 4, 6, 8, full valence shell. Iodine has 2, 4, 6, 8, full valence shell. 2, 4, 6, 8, 2, 4, 6, 8. Everybody has 8, except for hydrogen. Hydrogen only has 2, but that's helium, so that's still a full valence shell. Okay, nitrogen has 8, 2, 4, 6, 8, because those are there. So everybody's stable, everybody's full. This is asymmetrical, so polar. This is polar, non-polar, symmetrical, non-polar, symmetrical. Equal distribution of charge. All the electrons are balanced. Same thing here. Not balanced here. We're missing something, right? We're missing something here. So this is not balanced. This is not symmetrical compared to those two. So this is polar. Okay. The only thing I didn't ask, which I should have, is which molecule up here is nonpolar with polar bonds? And then which molecule is nonpolar with nonpolar bonds? So take 30 seconds, think about it. So which one up here, so obviously not this one. So out of these two, which one has polar bonds? Which one has nonpolar bonds? Talked about this yesterday. It's a good review, recording for people who missed, so that's good. Adam, what do you think? Very good. These diatomics, Hankelbrief, are the only 7 bonds, or 7 molecules, that have a nonpolar bond. Colin, what makes this a nonpolar bond? So the molecule is nonpolar because it's symmetrical and balanced, equal distribution. Why is this bond nonpolar, but these 4 bonds are polar? Need a phone a friend?
Yeah, phone a friend.
All right. Pick somebody.
Hannah, sure. If she's raising her hand.
Yeah.
James.
Because they have the same electronegativity.
Right.
It ends up 0.
Right. So the only way you can have a nonpolar bond is if the atoms are identical. Okay? So they both have an electronegativity of 4, so that's a 0 for a difference in electronegativity. Okay? Here, between I and C, I don't know what they are. Who looked them up? What'd you get for I?
2.7.
So I is 2.7. C?
2.6.
2.6. Okay. It's pretty close. It's pretty close. Okay? But there is a slight difference, 0.1. So this is actually very close to a nonpolar bond as well. But really, pure nonpolar bonds have 0. So yeah, 0.1 is almost 0. But this is pure nonpolar because it's 0. Those are the only ones that have a nonpolar bond. Every other bond in the world that's covalent is going to be polar because somebody's winning that tug of war. They're both fighting over those electrons. Remember, here they share unequally. In that bond between the I and the C, they share electrons unequally. Same thing here. Nitrogen is 3.0, H is 2.2, so that's 0.8 difference. So here, it's very unequal. So this bond is polar, that's polar, that's polar. All of these bonds are polar. That bond is nonpolar. The whole molecule is nonpolar. This whole molecule is nonpolar, but the bonds, again, are polar. I said it yesterday. I'm doing it again to help you try and understand that. All right? So what else did I ask? How many bonds? Oh, most polar right here. Biggest difference in electronegativity is the most polar. This one is the most nonpolar. Okay, so this is the least polar, most nonpolar. This is the most polar, least nonpolar. Bigger the difference, the more polar. Okay, This has 3 bonds, this has 1 bond, this has 4 bonds. How many electrons are being shared? 8. 2, 4, 6, 8. Those are being shared. 2 electrons being shared. 6 here. 2, 4, 6. So the dot and X in between the atoms are being shared. Here, everyone look up here. Here, these are being shared unequally in the bond. But overall, this thing is balanced, so it's equal. It is confusing, but I'm being as clear as I can. The whole picture, the whole molecule, things are being shared equally because it's balanced. But the individual bonds, it's not equal. There's a difference. This, it's pure equal. No one's winning, that's 0 difference. So they're sharing 2 electrons. They're sharing 2 electrons per bond, but again, they're sharing unequally because there's a big difference there. Okay? So, can you count the bonds? Can you count the electrons? That's important. Can you tell me which one's polar, non-polar? That's important. If you're really struggling with this non-polar molecule with polar bonds, I understand. That's confusing. That's kind of last on the list. Can you tell me who's non-polar and polar? Can you tell me how many bonds? Can you tell me how many electrons they share? Those are the more common questions. Last one. Who dissolves in water? I'll give you a hint. It's only one of them. NH3. Why, Mike?
Because it's polar.
Polar. Like dissolves like. Polar dissolves polar. Non-polar dissolves non-polar. Guys ever get ink on something? Pants, shirt? How do you get it out besides washing it? Anybody know?
OxyClean.
Yep. But besides that, you can actually use hairspray. Take a wet washcloth, like get it damp with water, then spray the crap out of the washcloth so it's like dripping with hairspray. Okay? And then you rub that on the ink spot and just keep doing that. It'll get the ink out. Why? Because ink is non-polar, hairspray is non-polar. So it gets the ink out. Water will not get the ink out because water is polar. It won't work. So water won't get stains out. Water won't get ink out. You have to use detergent or special kinds of solvents to get certain stains out. Soap is non-polar. It gets dirt out, stains out of clothes. But it's also kind of polar because water washes it away at the end. So the soap goes to the dirt, the stain, whatever it is on your clothes, and it dissolves it because soap is non-polar, just like the stain or the dirt or whatever it is. But then there's parts of it that water can actually wash away at the end. Otherwise, it really wouldn't work. So the whole reason things get clean is because of this polarity stuff, like dissolves like. All right, Matt, can you stop that actually? Because I don't want like a super long one. I'm going to